So we're on to the last part of our journey in LCR circuits. And I'm sure this is going to come as no surprise to you that we're going to be interested in a couple of things. One is we're going to be interested in finding the supply voltage once we know how the inductance, the capacitance and the resistance work together. And so I'm just going to dive in and show you how it works. So let's say we've set up a circuit and we want to know, well, what's the impedance of that circuit? Once we know the impedance of the circuit, we can find out how the supply voltage is behaving. So what we do is we can work out, using L and C, we can work out their reactances. Okay, 1 over omega C. And for this one, okay, and you need to be just a bit careful. You see my C starting to look like an L there. Don't fall into that trap. Omega L. Once I've done those two things, I can go, well, how am I going to find the total impedance of the circuit? And luckily for us, if we remember our phasor diagram from before, from our previous work, we know that the resistor voltage is just going to be out here, okay, at whatever point, okay, for our purposes. Our inductor is going to be however big our inductor is, our reactance of our inductor is. Sorry, that's an L, make it look like an L, okay. Sorry, I'll put R on that so that we know. And our capacitance is whatever our capacitance is, and that gives us whatever our reactance is of our capacitor. And I hope you can see where I'm going with this. We can solve this. We can resolve these phasors to tell us what the impedance of the circuit is. So I hope you can see that this is smaller. Okay, so I'm going to be able to shift this to here, and there's going to be this much total reactance in the circuit. So there's this much reactance from my capacitor, and the reactance from my inductor is cancelling a certain amount of it out. Okay, it's not a very nice way of thinking about it, but it's the easiest way of thinking about it. I know some of you don't really like vectors, so you're just going to have to, in your head, be thinking, how can I understand these two things? I've got this much going down that way. I'm going to use up that much of it, and what I'm going to get is a total overall reactance. And I'm going to just use this black to mark where I think it is. Obviously, I haven't used a ruler, which naturally you would do if you were actually drawing an accurate diagram of this. And here's R. So can I add together this portion of the reactance and the resistance? Yes, I can. They are vectors. I can add them together. And what I find is that I can get the overall impedance Z of the circuit. Okay, so I just drew a little diagram to show how that works. But what we would do, or what we'd be able to do, is solve this mathematically without drawing diagrams. And fortunately for us, it's just a variation on Pythagoras, which we are already excellent at. And we find that Z equals the square root, okay, and we're going to put these two here, XC minus XL squared, sorry, that's the squared, plus R squared. And I hope you can see how this works. It doesn't really matter which order you put the C and the L in. Okay, if this turned out that C was smaller and L was bigger, and you ended up with a negative number, it doesn't matter, you're squaring it anyway. It doesn't matter which way around these two go. What you're interested in is the difference between them. And the R squared, because R's not in the same line, in the same direction, we put that out by itself. So what we're saying here is, first, find the difference between the reactance of the capacitor and the reactance of the inductor, whatever that happens to be. Square that difference and add the square of the resistance, and we get Z. And this is nice and handy because we can then say, well, because we can just use I as you know, the same in all situations, we can say, well, in that case, we can use Ohm's law to say the same thing. Okay, with all my nice subscripts and superscripts beautifully done and not being at all ambiguous. C, L, and R. Okay, and we can do lots of problems with this. We can find Z, the impedance of a circuit, and we can use that to work out problems about the source voltage. We can draw a diagram so that we know how the source voltage, where it is. Does it lead the resistance or does it lag behind the resistance? In this case here, you can see that Z lags behind the resistance. So the source voltage is also going to lag behind the resistance. It will be out of phase and behind the resistance. However, it leads the reactance of the capacitor and it lags behind the reactance of the inductor. If the reactance of the inductor was bigger, Z would be on this side. Let's say we put in a really tiny a capacitor that didn't make a big reactance. So in our case, it would be obviously a large capacitor, gives you a small reactance. If it was really small, then Z would be, you know, dominated by the reactance of the inductor and the resistance in the circuit. And this is really useful in a number of applications, which I'm going to get to next.